Hello everyone, very honored to have this opportunity to share our method for NIR ISL 2021 and exchanges with you. My name is Hao Zhang, a postgraduate from Northeastern University College of Science, EyeCool Research Center. Today's sharing is divided into 5 parts. The first is an overview of our method. I will introduce the overall architecture of the method we used in the computation. The second is the key problems. We have summarized 3 problems that need to be solved in this computation. We think these 3 problems are the critical point of our method. The third is our solution for the 3 problems. I will describe the detail of each solution. The fourth is the result of our method, mainly to show the performance of our method, the model complexity of the CNN part. Finally, in the fifth, we review our method after the computation and then summarize its shortcomings and point the further research. Let's go to the first part. As shown in the figure, our method can be divided into 2 parts, a CNN part and a post-process part. The left is the CNN part. This part takes the iris image as input, produces iris mask for iris segmentation task, and the intermediate result for iris localization task, namely inner mask and outer mask. In this part, we proposed a boundary attention module and an improved UNet. The right is the post-process part. This part takes the inner mask and outer mask as input, produce the parameters of the input inner and outer edge of the iris. We use least squared method to calculate the parameters of the ellipse from the boundary of the inner mask and outer mask. The ellipse represents the inner edge and the outer edge of the iris. This overall architecture is the product of our continued improvement in the computation. Part 2. Key problems. Through the detailed analysis of the dataset provided by the organizer, combined with our actual experiment results, we have summarized 3 key points of the computation, and there are also 3 problems that need to be solved. Problem 1. The most accurate biometric method required a high-resolution mask, and how to get a more accurate iris segmentation result. This problem is not only important to the computation, but also important to the iris recognition. To solve the problem, we proposed an improved UNet. Problem 2. Hausdorff distance is very sensitive, and so how to enhance the robustness of our method for iris localization. Hausdorff distance is just one reason, of course. In fact, the accuracy and the robustness of iris localization are also a problem in practical application. For this, we propose a boundary attention. For problem 3, trained dataset are smaller than validation dataset, and how to get an effective model from such a small dataset. For example, CASIA iris complex occlusion and CASIA iris complex of angle only contain 100 image in the training dataset, but 400 image in the test dataset. It is difficult to train an effective model from such a small dataset. Finally, we use transfer learning to solve the problem. These are the 3 problems we summarized during the computation. Part 3, our solutions. As we know, UNet performs very well in biomedical image segmentation. It is also suited for iris segmentation. So, we use UNet as the base model of our method. It can be seen from the structure of this figure. Only a great UNet is not enough. We need a higher segmentation result. Then, we take a part of efficient at B5 as a powerful encoder. Doing this can improve segmentation performance significantly. Also, other CNN model can be used as an encoder too. In practice, we first use convolution with Straddle 2 to process the iris image. We use the first 4 stages of the efficient at B5 at the encoder. In the decoder part, we use bilinear interpolation to match the feature maps of different scales. For example, we upscale the feature map in the last stage of the encoder to match the feature map in the first stage of the decoder. That is the solution for problem 1. As for problem 2, we take inspiration from edge detection and face alignment task. As shown in the two formula and the figure, we use Gaussian filter to get the ground truth of boundary attention from the ground truth of the inner edge and outer edge. We name it heat map. Then we use the heat map as special attention, namely boundary attention. As here in the left figure, the heat map is used as special attention to the feature map with element y star, element y ahead. As shown in the right figure, we predict the heat map in the last 3 stages of the decoder. With boundary attention, the model can pay more attention to the edge of the iris. This operation not only makes our method more robust for the area localization, but also improve the accuracy of area segmentation and localization. Finally, for problem 3, we need to solve the problem for the scarcity of the trained dataset and further improve the performance of our method. So, we train a base model from all the dataset, then we fine-tune the base model on a different dataset. So far, the CNN part of our method is introduced completely, and we get an iris mask, an inner mask, and an outer mask. As mentioned in the first capture, then we use least squared method to calculate the parameters of the ellipse from the boundary of the inner mask and outer mask. The ellipse represents the inner edge and outer edge of the iris. That is all the detail of our method. Here are the performance and the complexity of our method. According to the result and the rank in the table, we can say that our method achieves an outstanding balance between the area segmentation task and the area localization task, and it also is a robust for a different dataset. The fifth part, summary. In computation, the first important thing is to obtain a higher evaluation result, and we did not pay attention to the practical value of our method. After the computation, we rethink our method. We found that it has great strengths and also some weakness. For example, the method is accurate for area segmentation and localization because of its great base model and powerful encoder. And our model is very robust, and that is because of the boundary attention. Also, the method has some weakness. The first is parameter redundancy. We believe that there is a lot of redundant parameters of our method, so it is too large to be used in real life efficiently. Followed the weakness 1, the second weakness is the slow speed of inference, of course. In summary, with strengths and weakness of our method, we believe it has great practical potential, and after the speech of other two teams, we think we should learn from especially the train strategy of them. That is to make our method perform better. In later research, we did do this work, so a light and real-time CNN model for area segmentation, localization, and recognition will be developed soon. Okay, that's all. Thanks for listening.